Section 5.2, linear approximations and differentials. Our objective is to use the tangent line to find the approximate values of f of x and the values of the differentials dx and dy. Actually, you did some of this on the homework that from the last section, you just didn't realize it. So this should be an easy thing. Let's jump into it and get it done. Local linearity, this is a concept that you've already been introduced to repeatedly. I've had in here y1 equals sine x and y2 equals x. And when you're zoomed in with a little tiny window, like what we have right here, then you can tell that right here they look to be the same. However, when you zoom your window out to a normal trig representative window, then they look like this. Okay, so locally linear means right in a small area, their values are very close to the same. Okay, they should be exactly the same at the point of tangency and really close thereafter. But the further you get away, the more the values differ. And you can tell as you get further and further out that your values are going to differ more. So locally linear means in a small region, not forever and ever. So if I'm given a function, f of x equals 15 minus x cubed, and I'm supposed to find L of x, that kind of looks like a 1, so you may want to rewrite it as L of x like this, or L of x, something so that you can tell you're still looking at a function of a line. That's going to represent the equation of the tangent line. We want to find that equation at x equals 2. We want to show that f is locally linear at this fixed point. So, like I said, all we're doing is finding the equation of a tangent line. You did that on the last homework, no big deal. We start off and we find f of x, or let's do f at 2, so that we know our y value there. And f at 2 is going to be 15 minus 2 cubed, so that should give me 7. So f at 2 is 7. Then I need to find f prime of x. That's going to be negative 3x squared, and f prime at 2 in order to find the slope of the tangent line at 2. So negative 3 times 2 squared, which is a negative 12. Okay. So my equation of my tangent line L of x is going to be negative 12 times x minus 2 plus 7. Easy enough. Y'all can do that. And when it says show numerically that L of x is a close approximation to f of x for values of x close to 2 by calculating the error in the approximation, what I did on this is that x values, I just let that be to where I would plug in the values I wanted, 1.9, 1.95. Okay, so I've got it on ask. y1 is my original function, 15 minus x cubed. y2 is my linear approximation, negative 12 times x minus 2 plus 7. And y3 is my difference between those. I did y1 of x minus y2 of x. And that way I can see the error. And so that you can tell right here at 1.9 my error is negative 0.059. So a little bit of error, but not a ton. As I get in closer, negative 0.01. Negative 6 e to the negative 4th. In other words, move that decimal back 4 places, so 0.0006. No error whatsoever at the point of tangency. And then you can tell we're moving away again. And so the further away you get, the more error there is, but the closer you are, the more likely you are to be very, very close to the actual value just by using that tangent line approximation. So that's what we're working on these, is trying to figure out exactly what that error is, how close we are, that type of thing. Okay, local linearity and linearization of a function. If you read something that says linearization, yes, my tongue is tangled this morning. of a function, then what that means is find the equation of the tangent line, and let's see how close. We want to use that to approximate the y value of our function. Okay? So the following, it's very important that we know that these are all equivalent. Again, this is L of x equals f at c, my point of tangency right there. Okay, that's the y value of my original order pair, plus f prime at c times x minus c. This is the equation of a tangent line that you've used forever. It's just that these two things are normally switched. Okay, so don't let that throw you. Not a big deal on that. Okay, I do want you to notice as you move down from one to the next, that what you notice is that x minus c right here is the same thing as dx. Okay, these equations are all equivalent, and so since the f at c stays the same, the f prime at c stays the same, x minus c is our dx. As you move down to the next one, f prime at c times dx is the same thing as dy. Now when you look over at the graph to the side, it's pretty easy to see that as far as the dx goes, I am doing that right here. X minus c right here gives me my dx, which is also the same thing as my delta x. Okay, so that's not a problem at all right there. We can remember those two things are the same. All I've done is subtract those values right there. However, if you notice, your dy and your delta y are two different things entirely. Okay? Your dy is the distance from f at c up to that tangent line, whereas your delta y is the distance from f at c up to the y value of the original function. And that little bit right in here is your error. That's how far off you are. That was what we got when we did our y1 minus y2, where delta y would have been like that y1 right there minus y2 right there. And that gave us that little bit of red, the error on that. Okay? Still should be always very close if we are close to the point of tangency. Okay, so I'm supposed to write an equation for the linear function L of x that best fits at x equal 1 when my f of x function is sine x. Okay, I'm going to have to pull in my calculator at this point because this is not a very fun problem to do without it. Let me make sure that my mode is on radians, and it is, so I am good. Okay, so let's go to y equals, and let's put in our sine x. All right, and then I'm going, because I'm going to need that, but then I want to go to my home screen, so let me do second quit and do sine at 1 so that I have that value. Okay, 0.8415 more or less. Okay, so sine at 1 equals 0.8415. And we continue on. Okay, but I'm going to go at least those 4 decimal places like that. All right, remember that's my f at 1, so now that I need to find f prime, I'm going to kind of scoot back a little bit. My calculator's taking up part of my space, so y'all just going to be patient here. So we have f prime at x, derivative of sine, which is cosine x. And so then f prime at 1 is going to be cosine at 1. So we'll put that in over here, cosine at 1. And I get 0.5403. Again, it does continue on from there, but we were going to do at least these 4 decimal places as I'm writing it. You may want to store those and hold those in your calculator. All right, and, okay, I'm sorry, I'm going to touch this and see if I can get what I'm seeing better. Write an equation for the linear function. So my equation, L of x, is going to be my slope, 0.5403 times x minus 1 plus 0.8403 0.8415. And we're running a little bit out of space there, but hopefully you can see that okay. Use that linear approximation to approximate f at 1.02. Okay, so that means come back in here and do L at 1.02. That equals 0.5403 times 1.02 minus 1 plus 0.8415. And again, this is going to be an approximation. If you've got your calculator handy, by all means, store these numbers and use them so you can get even more accurate than what I am fixing to get. Okay.
Morning Chorus Church, volunteers, leaders.
Okay, and if you caught that little bit of an announcement, then you can tell that I am up at school trying to get this done before church starts. So, yeah, sorry about that. I did try to pause it real quick so you didn't have to listen to the whole announcement, but for your enjoyment, we had an interruption. All right, let's plug it into our calculators and see what we can figure out here. Okay. And I'm just going to put this in as, let me see if I can do this. Go back up and hit enter, times 0.02, close parentheses, plus, you go back up and grab this one, enter, and that way it is more exact. And I get 0.8523 more or less. Okay. Okay, what is the error approximation? Let me pull back up my calculator because what I'm going to have to do here is f at 1.02 minus my L at 1.02. So I'm back up my calculator here. Let me clear all of this mess out, which I may regret having done, but we'll try it. I want to do sine at 1.02, close parentheses, minus my 0.85. Yeah, this is where I needed to have saved all those numbers. We're going to put in the 0.8523. Sorry, y'all. Where'd my parentheses go? I thought I put a parentheses in here, y'all. Sorry. Second, insert, parentheses. Okay. Okay, so e to the fourth, I am getting 0.0002, it looks like, on that. Okay, so if I do that percentage error, 0.0002, divided by the actual value of 0.8415 times 100%. And I just noticed that I had an error here because I had this right here. Sorry, put in your 0.8521 because that was your actual value. Right there, sine at 1.02, 0.8521, and you get 0.0198% error, which is not much error. That means we're doing pretty good. All right, and then it says, excuse me, what are the values of dx, dy, delta x, and delta y? If you go back and look just one thing back, if you notice dx and delta x are the same, and that's x minus c. So your dx equals your delta x, which equals 0.02 when you subtract 1.02 minus the original value of 1. Okay, that's where we get that. But your dy and delta y are two different things. Remember, dy is just going to be this little distance here, so that's your f prime at c times delta x. And so your dy is 0.5403 times your 0.02, which, grab my calculator here, 0.5403 times 0.02 is 0.010806. And our delta y is my value of 0.8521, the actual, minus 0.8415, the one that I got from my tangent line, the y value from my tangent line, right? Let me change my language detail. Y value from my tangent line right here, and my y value that was actually the value at 1.02. So my delta y is that right there. And if I subtract those, 0.8521 minus 0.8415, then I have 0.0106. And that is awfully close, within 2 tenths, hundreds, thousands, 10 thousandths. So therefore, I do know that my delta y is approximately equal to dy. Right? And that's our goal. Now then, tomorrow, when you come into class, we're going to look at, well, let's look at this just real quick and let you jot this down. Algebraically, when you're looking at properties, you want to remember that dx equals delta x and that dy is f prime of x dx. Verbally, we want to multiply the derivative by the differential of the inside function. That's what we mean on that. But now then, since I forgot that slide was there, tomorrow what we're going to look at in class is we're going to start with these right here, find them real quickly, and let y'all get going on homework. So see you then. Bye.